We're going to continue on our theme of first order kinetics. In our last lesson we talked about the integrated rate law for first order kinetics. Now we're going to talk about the concept of half-life. And you're going to learn to employ the concept of half-life and see the relationship between a rate constant and the value for half-life and be able to utilize those into calculations. So what is half-life? It's the amount of time, if you start with a certain amount of reactant, the amount of time it takes to drop that down to half of the amount that you started with. And we've got these symbols here to represent half-life. The half-life symbol is T1 half, and here is the statement above in symbols. The amount of time it takes to get your concentration down to half the amount you started with. So let's derive the half-life formula. This is our integrated first order rate law. And we're going to do some substitution. What are we going to substitute? We're going to take what this represents here. So we're going to substitute in half-life of A naught there. So this is going to give us this equation. Now, of course, the A naughts will cancel, and we have the natural log of 1/2 is equal to minus KT. Well, as we bring the minus to the other side, that actually gives me the natural log of 2 equals KT. And then we will actually calculate the natural log of 2, and that's 0.693. So this equation right here is our half-life equation for first order kinetics. So make sure as you commit this to memory that you realize that it only applies to first order kinetics. And it's helpful. I mean, you could maybe learn it from this stage if you could derive it kind of quickly. It's helpful to look at that in that derivation to help you remember this equation. Now, for my class here at the University of Kentucky, I require them to memorize equations that are in boxed form there. So this is one that I recommend that you commit to memory. So this is only for, again, first order kinetics, and it is independent of how much you start with. It doesn't matter whether you start with a lot or a little. It's the amount of time to take it however much you start with and drop it down to 1/2 its original value. And that's what that statement says. Doesn't matter how much time it takes. So let's look at this representation here. In the top sphere we see 16 molecules. Let's say that maybe each one of those represents a tenth of a mole. Then we could have a representation of a certain amount. As one time interval, whatever the half-life is, whatever that time interval is, the amount of time it takes to drop it down to 1/2 its value is its half-life. And what we see with first order kinetics is that time interval is exactly the same to drop it down to its next half as much. And that time interval is exactly the same to drop it down to its next half as much. And that's unique for first order kinetics. Of course, in our next time interval, how much will we have remaining? Well, there would only be one blue dot in my circle. So let's think about this problem, and I'm going to have you stop the video and ponder it. I have a first order reaction. I'm starting with an 8 molar solution, so there's its initial concentration. And the half-life is a minute. So I want you to think about how much is going to remain after 3 minutes. Did you say 1 molar? Well, if you did, you'd be correct. What are we doing here? If it's 3 minutes, we have 3 half-lives that have gone by. In the first half-life, it's going to go from 8 to 4. In my second half-life, it's going to go from 4 to 2. In my third half-life, it's going to go 2 to 1. So we're going down into those as we go through those half-lives. If we look at our picture, here we see that we have said that this is these time intervals are in minutes basically. And we're starting here with 8 and going 1 minute down to 4, going the second minute down to 2, and then in the third minute we're certainly going to go down to 1. So let's do a calculation here. We have a first order reaction and they've given me the rate constant. Now we know that we can obtain a half-life from that rate constant, 0.693 over K, which is 3.0 times 10 to the minus 3 seconds to the minus 1. Now remember, that's our unit for first order kinetics, always for the rate constant. So we can obtain our half-life from that formula. Now let's think about this. We want to know the time required for the reaction to be 75% complete. What happens after the first half-life? First half-life, it goes from 100% there to 50% there. And then it's going to go from 50% there to 25% there. That's cutting it in half again. That would be 75% complete. So this is asking how much time is it going to take to go through 2 half-lives. Well, if we knew how much time it took to go through 1 half-life, we'd be set. So what is 1 half-life? When we do this calculation, we find that it's 231 seconds. So it will take 231 seconds to go through that half-life. Now we really only know it to 2 significant figures, so we could say it is 2.3 times 10 to the second seconds, and that is 1 half-life. 2 half-lives would be twice that, so it would be 4.6 times 10 to the 2 seconds, or around 460 seconds. This problem is a little bit different in that it doesn't have a nice multiple of half-lives. It's 30% complete. Well, if it's 30% complete, what we're going to want to do, if we can't figure it out by a certain number of half-lives, is we're going to go back to our first order kinetics problem, or integrated first law. And this is really the first time we are seeing this equation being used. 30% complete is 70% still there. So what we know is if we started with all of it, that would be 100. And that's not a concentration, but this ratio would be the same. It works in percentages as well. If I started with 100%, if it's 30% complete, be very careful here, 70% is still there. So we've got the 70 over 100, or we have 0.7. And we figured out this is the same rate constant, so we know, actually we don't, doesn't matter, 3.0 times 10 to the minus 3 seconds to the minus 1 here, and we can solve for the time it takes to do that. So let's see here. We will obtain the natural log of 0.7, and that's a negative 0.357. We will divide both sides by negative 3.0 times 10 to the minus 3. And that will give me a t-value, a time of 119 seconds. Again, we really only know that to 2 significant figures, so that'd be 1.2 times 10 to the 2 seconds. Should it be less than the half-life? The half-life was 230 seconds. Well, yes, because the half-life is to get to 50% complete, and this is only 30% complete, so that number makes sense. Now, I want to go back to the previous problem for just a moment, because if you looked at this problem and you could not think, okay, 75% complete, that's 2 half-lives, you could work this problem in a similar fashion as the one before. And if you started with 100 and it's 75% complete, there's a 25 there. And then we have a negative k times t. And we could solve for t, and we would find that it would be the same value. So you didn't have to notice that it was 2 half-lives, but once you know the half-life, it's sometimes very convenient to look for that. Okay, so that finishes our learning objective. We've learned the relationship between half-life and k. We can utilize that to go between the two, and then use it in a calculation.